Morning, welcome everyone. My name is Aleksandra Laskowska, and today I'm going to talk about majority coloring of undirected graphs and a game based on that concept. During this short presentation, I'm going to introduce you to the theory of majority coloring. Then I'm going to present a game based on that theory. I'll show you my motivation, rules, and difficulties that I needed to overcome during implementation of my idea. And at the end, I'll sum up this presentation and suggest some interesting readings, perhaps. So first, I'd like to highlight that every time I say graph coloring, I will be referring to vertex coloring. So please do not be confused by that. So what is vertex coloring? It is simply assignment of a color to each vertex of a graph, and in order to satisfy proper coloring condition, we need to color a graph in such way that no edge connects two vertices in the same color. So now take a look at the image on the left, and the figure at the left. And there is an edge over here connecting two vertices of the same color, and as well here there is an edge that it is monochromatic one. So surely we can say that this coloring is not a proper coloring, whereas the graph on the right is properly colored, because we can see that there is no edge connecting two vertices of the same color. And the minimal number of colors needed to color a graph properly is called the chromatic number. As you can see, a chromatic number in our example is 3, as there is no as it is not possible to color it properly with less than 3 colors. Now that we are familiar with the idea of graph coloring, we can move on to majority coloring. So here we go. We say that an edge is a good one if it is non-monochromatic, and on the contrary, an edge is a bad one when it is monochromatic. As simple as that. And we also say that a vertex is happy if it is incident with at least as many good edges as bad edges. So in other words, at least half of incident edges must be good, and otherwise vertex is sad. Now a coloring where all the vertices are happy is majority coloring. And similarly to proper coloring, the least number of colors needed to color a graph in such way, in majority color way, is called majority chromatic number. So let's now take a look at this graph over here. We can see that there are some bad edges, like here, 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 many of them. So let's mark them dotted lines. With dotted lines. So now we can see more clearly. And now let's see which ones of those vertices are sad or happy. Okay, so we can see that there is a sad vertex over here and sad vertex over here, and this is because all of its incident edges are bad ones, and here 2 out of 3 incident edges are bad ones. So this is more than a half. So to fix the situation, we will color this little guy over here blue. And as we can see, it made him happy. And this one over here also is happy because now it has 2 out of 3 incident edges that are good ones. But let's check over here that there is still some sad vertex. So we can just change the color, and now we obtained a happy face. So our coloring is majority coloring. And please note that there are still some bad edges here, but it is completely fine with majority coloring because it is simply not proper coloring. So this brings us to the conclusion, maybe more as an observation, that majority coloring does not have to be a proper coloring. So proper coloring is, of course, majority coloring. However, it does not work the other way around. Okay. Now, let me introduce a simple but fantastic theorem found by Hungarian mathematician Laskowska. Apologies if I mispronounce this name. So the theorem says that every undirected graph can be majority colored with only 2 colors. And in order to do so, we simply need to maximize the number of good edges. And the process cannot go on forever, so in fact, at some point we will obtain majority coloring. So in fact, it is basically what we did in our previous example. Okay, now that we know theory, we can move on to majority coloring game. So the motivation...
You'll need to unlock your iPhone first.
Okay, I'm sorry. That was Siri. The motivation behind it was to create something to popularize and educate on graph theory. And the rules, I believe, are simple. Hence, everyone can play it regardless age or background. So the rules are as follows. There are 2 players. One tries to majority color a graph, while the other one is trying to prevent it. So I wanted this game to be a single player game. So I replaced the second player with an algorithm that chooses a vertex based on users' moves. And the idea was inspired from a paper written by Polish mathematicians. It was written in 2018, and as you can see, the title is Majority Coloring, so you can check it if you like. Okay, so now I'm going to switch to the game view to show you what I'm talking about. As it happens, I have it open here, and it is available online. Current level you can see over here, and there are 5 levels, as you can see. And this is the first one. So it is a very, very simple graph. I want this to be first, user acquaintance with the rules and the game. So I wanted to make it easy. So a user, so in this case us, me, only have green color to color vertices, while the opponent has red vertex, red color to paint. We can change a color of the vertex by simply clicking on it. So let's do it, yes. And as you can see, as soon as we clicked a vertex, and the opponent will choose a vertex to color it red. Okay, so I'll keep playing, and that was easy. We obtained majority coloring, so we can now move to the next level, but instead I'll move back to the presentation to say a couple more words about my work. So during implementation of this game, I needed to address two issues. The first one was to come up with efficient strategy of an opponent, and the second one was to compose graphs that are neither too easy nor too difficult to play. So speaking of an opponent strategy, let's compare two algorithms. So on the right side graph, an opponent would choose this vertex V, to color it red, and this choice will lead indeed to create one monochromatic edge, right, this one, but also one good edge like this one. Whereas the first graph, the graph on the left, we can see that the choice is different, and here one monochromatic edge will be created for sure, but also two others will be created for sure as well, because either this edge or this edge will be non-monochromatic, and either this edge or this edge will be non-monochromatic as well. So it depends on which color will be assigned to this vertex or this vertex, but either it will be red or green. There will be for sure one more bad edge. So we can see that this strategy is definitely more efficient than that one. However, this algorithm was implemented, the simpler one, and the reason is just that in case of this strategy, it wouldn't be possible to win and to majority color a graph on level 2 already. So it would be too difficult to win with the opponent. The opponent would outsmart us every time. Yes, so this is a fun fact. Okay, now what is also interesting that it gets more difficult to win if there are many adjacent vertices with odd degree. And to understand what I mean, let's consider this scenario. So let's say there is a red vertex V, and that has odd number of neighbors. So V will be happy when at least n plus 1 of its neighbors are green, right? Remember, we can only use green color, and our opponent uses red color only. And so, for example, if V has 3 adjacent vertices, we need 2 of them to be green to make V happy, right? At least half of them. So in this case, n plus 1. But let's assume that let's say that our opponent has made the first move on V's neighbors and colored it red. So this now will give us 1 red neighbor and 2 n blank neighbors, 2 uncolored neighbors, 2 n uncolored neighbors. So now we have to act fast and color next neighbor green, but then the opponent will color next neighbor red, and we will color next green, and then red, green, and so on and so on and so on. And this in result will give us n green neighbors and n plus 1 red neighbors, which will make sadly v sad. And game over. And what's more, if one of those red neighbors of v will have odd degree as well, it might be even impossible to win sometimes. Yes. And this is exactly the case that that you can see on the final level of majority coloring game. This graph over here is the final graph in my game, and it has a majority coloring, as you can see. However, it is not possible to achieve this in the game because of the opponent that doesn't let us make it happen. So don't even bother to try to go through last level. Okay, to sum up, I think there is a great potential for research and educational tools in graph theory. I hope that I have showed this today, hopefully. And note that I was focusing only on undirected graphs. However, there are many variations of majority coloring, and one of them, like T graphs, directed graphs, you can see in further readings that are included here. And there are some interesting open questions included there. So please check it if you are interested. And if you like the game, you can just go ahead, don't be shy, and scan the below code. You can play it either on your phone or on your computer. I think computer would be better choice, but phone is good as well. Okay, thank you very much for your attention, and have a wonderful rest of the day. Bye.